the value of money today is not the same as the value of money in a year from now. So imagine we get a dollar. What is worth more, the dollar we get today or the dollar we get a year from now? Well, the dollar we get today, we could invest it and we could potentially make more. And the value of the money we get a year from now, we can't invest that for a whole year. We lose that whole year. So money is constantly losing value, and this is called the time value of money. And the way we counteract that is this thing called interest, and banks use this to mitigate risk as much as possible, right? So this is the formula for discrete compound interest, right? So this is the interest per year, and this is the amount of years. This is the rate, right? And this is the payments, the amount of payments within that year. If we take the limit of this, if I take the limit of this, we get E RT, right? And this is a common, if you simplify this, this will be a common limit, right? But we could go deeper than that. We could actually derive continuous compounding with differential equations. So let's say M of T represents money at time T. And let's say money at time T plus the amount of time until our next interest payment, that would be equal to money at time T plus our rate times the amount of time till our next payment times money at time T, in which these two are pretty much the same thing. You could see. Now, let's try to move all these delta t's to one side so we could do this limit type thing. So, first we take this, move it to this side. Money at time t plus delta t is equal minus money at time t is equal to r delta t mt, right? And then we could move this delta t to this side, so mt right. Now, what does that look like? That looks like the definition of a derivative. And perfectly enough, if we keep decreasing the time interval between each interest payment infinitely close, that would be the derivative, right? And that's the same thing as doing this, but instead of taking the limit as m approaches infinity, we could do a limit as delta t approaches 0, which that's the derivative, and this is the exact rate of change of our interest, right? So then we could simplify this to be dm dt is equal to r m, right? I took out the with respect to t because I don't feel like writing that. And we could give it the initial condition of m at 0 is equal to m naught, right? So with that, we could just solve it. It is separable. It's an easy equation. So dm dt, we can move this to this side. Rm is equal to 0. Actually, no, let's not do that. I don't think that's right. We could keep it like this. We want all m's on one side. We want we want all the m's on one side, and we can move the t to this side. So then we could do, let's get another page. So let's move all the m's to one side. 1 over m dm dt is equal to r, right? And then we can move this dt because it's separable. 1 over m dm is equal to r dt. What? Now this is easy to solve. We could take the integral of both sides. Integral of this is just ln of m, and that is equal to the derivative of this, which is just rt, and then we could do the plus c here. That's technically as a plus c, but that you could just combine those two, and then we have 1 plus c here. Now, to solve for m, our money, how much money we'll have, we just take both to e, right? These cancel out. We have m, and that is equal to ERT times EC, right? And yeah, so that's the rule from this. So this is addition. That simplifies to that, right? Okay. So now we could think about our initial condition again. What is a c? If, remember, this is to the respective time. Let's not forget that. We know that m at time 0 is equal to e r times 0 times ec, and that's equal to e of c. And we know e of c, m at 0 is equal to m naught. We could just say these are the same, and then we will get our final differential equation. Where is it? Okay. m at time t is equal to m naught e r t. And that's the same thing we have with taking the limit of m right there. And we also have our principal, which I didn't give us a principal here. So normally there would be a principal there, and that would be principal p, right? So this is continuous compounding, and that's why it makes sense. And this is what most banks and everything use. We use continuous compounding. Discrete compounding doesn't really happen as often.